Good evening, everyone. It is now 5:30. We're going to wait a minute or two for folks to join us, and then we'll get started with tonight's public talk. All right, good evening. We're going to get started with tonight's talk. My name is Roy Gal. I'm an astronomer at the Institute for Astronomy, and I'm going to be your host for the evening. Before our speaker starts, I wanted to tell you about some upcoming events that we have that you might be interested in joining us for. This Saturday, December 4th, from 3 to 9 p.m., we'll have a Makahiki Games and Stargazing Festival out at Ala Moana Beach Park, a magic island in the area near where the red stars are on that map. And we will have various Makahiki games and crafts. It'll be kid-friendly. We'll be viewing the sun during the day and switching to stargazing at night. And this is a free public event. It's one of the first public events happening in the parks since reopening. You will need to be vaccinated or show a negative COVID test to attend. But we welcome everyone to come and join us, and we're looking forward to having public events again. So that's this Saturday from 3 to 9 p.m. And please let your friends and family know. And if you're interested in the topics of astronomy and James Webb Space Telescope, our final talk in our Hawaii Webb Space Telescope Connection Series will be next week, Wednesday, at the same time, in the same URL on YouTube and on Zoom. And Chris Ashall, one of our postdoctoral researchers, who was one of the few people with 2 approved first Cycle 1 James Webb Space Telescope observing programs, will be talking about unveiling exploding stars, a supernovae, with James Webb Space Telescope. Today, you're here to find out about infrared detectors from JWST and beyond, and some of the science that is going to be done with those generations of detectors. And our speaker is Michael Bottom, an astronomer at the Institute for Astronomy. I'll tell you a little bit more about him. I'd like to encourage you to sign up to get our electronic newsletter and announcements of events like this at the URL that's on the screen, and to follow us on our social media channels, Facebook, Twitter, YouTube, or Instagram. We're IfA everywhere. So a little bit about our speaker. So Michael Bottom lives in Hilo, Hawaii. That he's at our Hilo facility. The Institute for Astronomy has its headquarters in Manoa, in Honolulu, but we have facilities in Hilo and on Mauna Kea and Haleakala and Pukalani, Maui. And he received his bachelor's in 2008 from Columbia University. He and I are fellow Columbia alums. But then he took a break from academia and went to be a stock trader on Wall Street during the financial crisis. So he's got some real world experience in addition to staring at the stars. Then he returned to school to get his PhD, which he received in 2016 from Caltech, which is also where I got my PhD. So we're academic siblings. And then he worked for years as an engineer at NASA and joined the Seth Institute for Astronomy in year 2019. And Mike is going to take over the screen and start telling us all about infrared detectors.
Thank you, Roy.
Oh, I'm sorry, Mike, to interrupt. I did want to say that we have 2 other panelists, Klaus Hodap and Shane Jacobson, who gave our previous talk, and they'll be available to answer questions along with Mike at the end of the talk. And you can put questions into the Q&A or the chat, and we'll keep an eye on those.
Okay. I hope everyone can see my screen. It should be a blank slide. Thank you, Roy, for the nice introduction. It's a pleasure to be here tonight with you. My name is Michael Bottom, And as Roy said, I'm an astronomer at the Institute for Astronomy in Hawaii. This talk is called Infrared Detectors Beyond the James Webb Space Telescope. But I thought it would be good to spend a good chunk of the talk giving a bit of background about why we actually need anything better than the already excellent detectors we have for the James Webb Space Telescope, which were developed in large part by our other two panelists here, and which will launch into space in the next month, so very soon. But the motivation for why we'd actually want to do any better is actually motivated by a very old question. So it's actually the question of whether there are other planets like the Earth. This is quite an old question you can see in the 4th century BC, an ancient Greek philosopher said that it was absurd to consider the Earth as the only population in infinite space. And more than 2 millennia later, these ideas were still being put forward. But at the time, these were mostly philosophical arguments because there wasn't any science or data to back the question up, or the answer up rather. So we can sort of break it up a little as a scientific question. It's a 2-part question. The first is, are there planets around other stars? And the second part is there life on those planets? Are there plants and animals? Are they populated? That's the 2 parts of the question. So the first part, we know definitively the answer to that. And that's been discovered in sort of the last 30 years, I'd say. There are absolutely planets around other stars. And the best way we have to discover them is actually to watch the brightness of a star over time. And then when an orbiting planet passes in front of it, it causes a tiny dip in the starlight. This dip is usually well less than 1%, but it's not hard to measure that signal anymore. And you can plot this and you can see as a planet passes in front, there's this very characteristic U shape. And you can see this repeat every time the planet passes in front of the star. So this has found something like 4,000 planets this way. And we now know that planets of Earth size and larger, slightly larger than Earth, are very, very common around stars. But is there life on those planets? That's the second part of this question. And that is a very, very difficult one to answer. Now, we can say that there is an answer. The answer could be yes or no, but we have to break it down to something that's a little bit more manageable for what we can do today. So maybe we can say, could life as we know it exist on those planets? Now, we have some idea about what life on Earth here needs, and that's where we can formulate this again, maybe even a slightly more specific way. Could liquid water exist on the surface of the planet? We know from life as we know it, that it requires water. And it's not maybe a huge stretch to say on Earth, wherever you find liquid water, you find life. So maybe it's true also on other planets. Now, if you think this is really, kind of a stretch because you're saying, okay, there's liquid water, then there's life. You're right, but we'll do a little better later in the talk. The question of liquid water, incidentally, has to do fundamentally with the temperature of the planets. If the planets are too cold, any water would freeze. And if the temperature is between, say, 0 and 50 Celsius or 0 and 130 Fahrenheit, then water may exist on the surface if it's there. If there is water, it would be in a liquid form. If it's much hotter than that, then the water would mostly turn to steam. So this is not a particularly popular way of describing planets. Astronomers like to categorize things incessantly. I actually just learned this making this talk, but these are different ways of classifying planets based on their temperature. But you can actually extend this notion of the temperature needed for liquid water to something called the habitable zone. And that's the orbital region around a star in which a rocky planet can possess liquid water on its surface. So it's not too close to the star so that all the water boils off, and it's not too far away from the star such that all the water freezes. This idea is pretty old, but actually it's in recent years has really been invigorated from all the discoveries. But it's not just how far away from the star the planet is. It's also the size of the planet that matters. If the planet's too large, the planet becomes a gas giant, like Neptune or Jupiter, and the notion of a surface ocean is not possible anymore. These are gas planets. They don't even have a well-defined surface. If it's too small, then the planet can't support an atmosphere. So if there's no atmosphere, then there wouldn't be anything to protect the water from the irradiation from the surface. Obviously, without an atmosphere, you can't have life. So really, current thinking is that a planet somewhere between about Mars size and twice the Earth size is the appropriate range of sizes to be potentially habitable. So this is what here we refer to as sub-Terran and super-Terran planets. So this begs the question, how common are rocky planets in the habitable zone? And actually, we can extrapolate results to know the answer. And it's about one rocky planet in the habitable zone per star. This is based, again, on an extrapolation of these results known from transits, which tend to find planets that are much too hot. But this is kind of an astounding result if you think about it. But one thing to note is that we haven't actually discovered so many of these planets. But let's turn back our attention to the solar system and look at the habitable zone in our own solar system for a moment. Venus is considered to be at the inner edge of the habitable zone, so just within it. And Earth is at the center, and Mars is also in the habitable zone. And if you saw these planets through a transit, you could tell that information. But the thing is, that doesn't give you all the information. If you look at these planets, they're all in the habitable zone of the sun, but they are dramatically different in actual habitability. Venus has a temperature that's hot enough on the surface to melt lead. There's a picture taken from a Soviet probe of the surface of Venus. Doesn't look like a very good place to be. Earth has a pretty good surface temperature, particularly here in Hawaii. And Mars is actually a freezing desert. So it's close to -80 Fahrenheit. So you can't get this information just from a planetary transit. What you need there is more. You need to actually take an image of the planet, and then use that image to characterize those planets. So what an image of a planetary system looks like is shown here on the left. I've blocked out the central star. I actually took this data from Keck a few years ago, the Keck telescope. And the central star is blocked out, and you can see 4 sort of orbiting planets. These are kind of huge planets. They wouldn't be candidates for habitability at all. But the idea that we're developing now and the techniques we're developing now are going to apply also when we take pictures that look like this over here with Jupiter, Earth, and Venus around other stars in the future. This is simulated data, obviously. So discovery of rocky planets in the habitable zone and their characterizations is actually considered one of the most important goals in astronomy for the next 20 years or so. And so this talk is going to talk about exactly how you do that and the critical role that the infrared detectors play in this. When you get the light of the planet separated, as I've shown this image, what you need to do essentially is characterize. And the way you characterize that is you take the light of the planet and you separate it into its component colors, which lets you learn a tremendous amount about it. And to explain that a little bit better, we have to go back a little bit to the basic physics of light. So light is a wave, and the different colors of light are related to their wavelength. Violet light has a wavelength, which is to say, if you held up a little antenna and measured how the current changed from a light beam, from crest to crest, that's one wavelength. And violet light has something like 62,500 waves in 1 inch. Then green light has something more like 46,200 waves per inch. And red light has 38,200 waves per inch. Red light has a longer wavelength. Violet light has a shorter wavelength. And it turns out that glass, this was discovered through a prism, which is a device that bends light. And it turns out glass bends violet light more than red light. As you can see here, you start with white light. It's separated in its component colors, and the red light bends less than the violet light. What's interesting is that there's more colors of light than we can actually see. This was discovered in 1800 by William Herschel. What he did was he wanted to see if the different colors of light had a different temperature. And he hooked up a thermometer and he dragged the thermometer over a rainbow that he generated from a prism. So he took sunlight, separated out into its component colors, and generated a little rainbow. And he stuck the thermometer in different parts of this. And you can actually do this experiment for like a science project. You just need 3 cheap thermometers and you color the bulbs black. And then you can see that different colors have slightly different temperatures. But what was interesting is he actually stuck the thermometer past the reddest light he could see, and it actually heated up even more than anything from the light colors that he could see. And that was actually the discovery of infrared radiation. Interestingly, if he had stuck the thermometer on the other side of violet, he would have discovered ultraviolet radiation as well, which would have been even more impressive. But it took people 1 year to realize that you could do that. So ultraviolet was discovered in 1801. I should also say that the concept of infrared and ultraviolet are sort of human-centric concepts. If there's not really a hard limit between these wavelengths. If Herschel had like a pet snake, for example, the snake wouldn't have been surprised by the thermometer heating up past the red wavelengths, because snakes can generally see in the infrared. And any insects in the room would have been able to see colors past the violet. So these are sort of fuzzy concepts, but they are useful for what will come next. This kind of opened the door that, you know, there's a ton of light that we can't really see. And this isn't just, I mentioned the visible and the infrared and the ultraviolet, but there's actually everything from gamma rays down to radio waves is a manifestation of the same phenomenon, which is electromagnetic radiation, also known as light. And the wavelengths change by quite a bit. Visible light, like I said, is about 400 nanometers, or like maybe 50,000 waves per inch. But it goes from something like the size of an atomic nucleus to something the size of buildings for radio waves. Humans, incidentally, can only see a small fraction of this. We can only see somewhere between, in the visible, obviously, but we can build instruments that can see other wavelengths. And light can tell us a lot about an object. And one concept that to introduce here is the notion of a spectrum, which is saying how much light of each color there is. So you can generate this, like I said, by putting light through a prism and seeing how intense the light is as a function of position. So for example, this is a beam of sunlight passing through a prism. And you can see that there's past red, there's nothing. So we draw a 0 over here as a function of wavelength. Then the red is pretty dim, so we trace it out over here. The brightest part is yellow, traced out by this light. Then it gets fainter as you get towards the blue, and rapidly fainter as you get towards the violet. So that's what a spectrum is when astronomers refer to it. And if you string a lot of prisms back to back, you can see some really interesting stuff. So let's take the spectrum that I just showed here, which is sunlight, and put like maybe more than one prism in a row. You actually start to see really interesting things. You can see that the light splits and it's not continuous. Now there's these sharp lines that appear in the spectrum of the sun. And you can see here in this plot that I've approximately lined up where the lines are with the intensity. So there's a dip in the intensity of light right here around 425 nanometers. And then there's another dip here. There are 2 dips here. There's one sharp dip here. And this is shown in the graph where it gets fainter. Intensity here is on the y-axis and wavelength is on the x-axis. So you can also, what's really interesting is if you compare this to the spectra of different elements. So what you can do is you can take a incandescent bulb or any sort of light, really, pass it through a gas, and then spread it out with a prism, and you get something similar. You get this spectrum of continuous color, but then there's also lines missing. So people started doing this sort of in the 1800s, and you can see, for example, hydrogen, helium, sodium, and calcium and iron. And these sort of deep absorption features are caused by the elements themselves, and they're sort of like a little fingerprint of what each element is. And if you take these known spectra and you measure that you've measured here on Earth, and you compare it to the spectrum of the sun, you can cross-match it and see what the sun is made of. So for example here, this is the sun spectrum that I showed in the previous slide. You can see that this line, for example, corresponds very likely to hydrogen. This one as well to hydrogen. This one corresponds to hydrogen, this one to helium, this one to helium as well. I might have not lined it up exactly right. But this is sort of like getting the DNA of something. It tells you exactly what the object is made of. The darkest and most intense lines in the sun's spectrum are from hydrogen and helium. And what's interesting is that the sun is actually mostly made of hydrogen and helium. And this wasn't a well-known fact, actually. Previously, people thought that the sun was made of the same stuff as the Earth was. And the person who set them straight was this astronomer, Cecilia Payne-Gaposchkin, about 100 years ago during her PhD thesis, which was probably the most important written in the history of astronomy. Nothing really made sense before that. And another interesting sort of factoid is that helium wasn't discovered on Earth first. It was first discovered in the lines of the sun. And that's why it's called helium, like Helios, after the sun god. And so it was an element that was discovered in the stars rather than on Earth. But you can do the same with planets. Here's a spectrum before, like I showed, of the sun. And there's also the spectrum of the planet Uranus overlaid underneath. And you can see, unlike stars, which have like really sharp lines in the spectrum, the planets have much more fuzzy and sort of deep features. And the reason for this is that they're mostly made of molecules which absorb a lot more light. The stars are so hot that they rip apart molecules, but planets don't do that. They're cold enough that molecules can survive. And so the molecules are pretty big targets, and so they have this really broad and diffuse absorption features. For example, in Uranus, you can clearly see the feature here of CH4, which is also known as methane. You can also see some features of water and other things. You don't see much water on the sun, obviously. And what's also true is you can not just do it to planets in our solar system like Uranus, but you can also do it to exoplanets, which is to say planets orbiting other stars. Now, there's a few caveats here. First, you have to reduce the glare of the star, like shown in this image, really with specialized instruments, so you can actually separate the planet light and make it stand out. But if you have the light of this planet clearly separated, as I've shown here, and you put it through a prism, you can get your spectrum of your planet. And that'll tell you what the planet's made of. Now, you might be thinking I'm kind of pulling your leg a little about all this prism stuff, but trying to simplify it for the masses or whatever. But here's an engineering drawing of the most, an instrument for the most advanced space telescope ever designed for exoplanet imaging called Luvoir. And in the middle, you can see it's just 3 prisms. So yeah, it's 3 instead of 1, but it's the same idea. There's a few lenses after and before to focus the light, but it's really the prisms that do all the heavy lifting of splitting the light into its different colors. So I haven't really been exaggerating much here. It's not much different from William Herschel's time. Except the instrument cost $300 million. But anyways, what about the Earth? So we're talking about Earth-like planets. Here's a spectrum of the Earth, which is overlaid with the optical part up top as before, where we can, this is the part where we can see pretty clearly. And in this case, my apologies, the x-axis now isn't in nanometers, it's in microns. So you have to multiply everything by 1,000. So 500 nanometers, 600, 700, 800. Our vision cuts off around 700, actually, but the optical spectrum usually is considered to go up until 900 or 1,000. The optical, we can't actually see 900 or 1,000, but that's a separate issue. Now, the question is really, what could you learn from a spectrum of the Earth? What would you be able to learn if you got a spectrum like this out of your telescope? So first, you can see the blue sky. That's this steep rise at bluer wavelengths. So this is the bluer side. And that tells us how thick the atmosphere is on the planet. So remember before we talked about how you need to know the planet has an atmosphere. You need to know how thick the atmosphere is to know whether the planet has one that can protect the planet without being too thick, or whether the planet is just a bare rock. Then we see the same sort of deep molecular features that we did that I showed before. And these are due to molecules which may ring a bell. Oxygen, needed for life. Carbon dioxide, a key element used by plants and also potentially indicative of volcanic activity. These molecules are called biosignatures, incidentally, because they are key to life as we know it. You can even do better than that, actually. So there's this sharp jump at around 760 nanometers, or 0.76 microns, which is unexpected. And this is due to plants reflecting infrared light to keep themselves from overheating. And the methane, the CH4 we detect, that indicates the presence of anaerobic bacteria, which is mainly due to livestock and other agriculture on Earth. So if you know what to look for, you can actually tell that the Earth is a living planet from its spectrum, or at least have very, very strong evidence of that fact. Now, one thing to note is that most of the deep and interesting molecular features that suggest habitability and the presence of life, like water and methane, are all at infrared wavelengths over here, which I've shaded. So this is where infrared astronomy comes in. To detect and measure these things, we need good infrared detectors. And how good? That's the next part of this talk. So I have to jump back a little bit into the physics of light to sort of explain some of the other aspects of this. One of the most surprising discoveries of the last century was that light arrives in discrete chunks, which is actually very, very much like raindrops. There's a minimum detectable unit of light, called the equivalent of a raindrop, called a photon. So for example, you can't detect half a photon, just like you can't detect half a raindrop hitting your face. Either a raindrop hits your face or it doesn't. And just like raindrops, light arrives sort of semi-randomly. You might be getting 5 raindrops a second on average on your face, but some seconds you might get 3, some you might get 7, etc. So you can think of each star or planet in the sky as putting out a steady stream of photon rain, if you will. And how brightly we perceive them to be depends on the rate of photons that are arriving. A bright star is like a heavy rainstorm, and a faint star is just like when it's spitting. So to put it quantitatively, for a very bright star overhead, like Arcturus, or known as Hokulea here in Hawaii, which is pointed at by this green arrow, you get something like 3.5 billion photons hitting each square foot of the Earth every second when it's overhead. That translates into about 1.2 million photons per second hitting your eyeball, since your eyeball is a lot smaller than a square foot. For the faintest star you can see, it's more like 13 million photons per square foot per second, or 5,000 photons per second hitting your eye. That actually might seem pretty bad. You're like, oh, the faintest thing you can see puts out 5,000 photons per second. But remember, your eye is updating at 50 or 100 times a second. So it's really more like 100 photons is the minimum your eye can detect, minimum bunch, if you will. And most of that is actually your brain filtering out the really faint stuff. Your eye is actually an extremely good detector. Okay, but what about a planet around a nearby star? We talked about how bright stars are, 13 billion, 10 million photons per second. What about a planet like the Earth orbiting a nearby star? How bright is that? And how bright is it? Can we detect trees and cows, etc.? And the news is not good at all. So a typical planet like the Earth would put out something like 10 photons per square foot per hour, not per second, per hour. And that's over everything. So you have to divide that up into, maybe you get one photon in this chunk, one photon over here, one photon over here, one photon over here. So it's really, really, it's really, really bad, not good. So you basically have two things you need if you want to be able to do this. First is you need a huge telescope. This space telescope concept I'm showing has a mirror 50 feet across. So it's about 2,000 square feet of a collecting area. So instead of 10 photons per hour from the planet, you have something more like 20,000 photons per hour, or maybe 5 photons per second, if you will. And that's assuming no loss in the telescope. So in the telescope, you might lose a very good fraction of those through the instruments and equipment you use to suppress the starlight itself so that you can see the planet. But it also turns out that what you really need is a good detector, something that can detect single photons. And multiple studies have shown that the most important factor for doing this kind of work, the single most important thing, is the detector noise and how good your detector is. So how do detectors work? So this is a sort of typical optical detector. And what you get is your photon rain coming in, and different pixels get hit by different photons. So a photon will hit the pixel and create one electron. So one photon creates one electron. And electrons are easier to work with than photons because you can use electronics to move them around. So your photon hits your pixel, and then you create an electron. You measure that electron, or photoelectron, if you will, by electronics. So what does that look like for ultra faint imaging, like something like a planet? So here's a simulation I put together, which shows what an image would look like with just about 1/10 of a photon per frame on average. This is with a perfect detector. So you can sort of see these random hits or semi-random hits, which are the individual photon events, very much like rain. So think of each pixel as like a little rain gauge, and whether it collects a drop or not. Mostly it collects 0 drops. Sometimes it collects 1, sometimes it collects 2. So it's very hard to tell from this image what you're actually looking at. It's not clear at all. You see that there's some kind of structure over here, if you can see my cursor on the center, and there might be some kind of structure up here at the top left, but it's not clear really what it is. What happens if we go to 1 photon per frame instead of 0.1 photons per pixel per frame on average? Then you start to get a better picture of what it is. Now notice it's not the same in every frame. As I mentioned before, it's like rain. Sometimes you get 5 drops, sometimes you get 7 drops, sometimes you get whatever. But you can sort of start to see that there's some kind of fuzzy animal that's being measured here. And you might see there's something else up here on top, but you can't really tell what it is. But the bad news is that detectors aren't perfect. So instead of getting, here's a picture I took from my cell phone of a perfectly dark room. I just turned off the lights and covered the sensor with my hand. So it looks like what it should, right? It doesn't really, it just looks black. So you should expect everything to be 0 because there's no photons hitting it. But if you stretch it out a little bit, you see that there is actually a lot of stuff in the image. And all this stuff is not real. You might say, oh, he didn't, he left some light on, or, the light's getting through his hand or something. But no, it's perfectly dark, but you actually measure a lot of photons. So if you zoom in here, you can see that some pixels measured 6, 10, 20, whatever. Maybe this one measured 0, which is what the true value is. But none of this is real. This is all just created by electronic noise in the detector. So let's go back to our image of our furry friend here. So this is with a perfect detector, what you'd get with 1 photon per frame on average. 1 photon per frame is incidentally about what you expect from an extrasolar planet like the Earth. And let's add a realistic level of infrared detector noise. That's what you see. So you can stare at this and you can sort of tell, I think, that there's something going on here. Like there's a little blob where I'm circling and maybe something here. but you've totally lost the ability to see the cat. And yes, it was a cat. And you can totally not even tell that there's something, maybe if you're really lucky, in the top left corner. Now, it's true, you could average like 1 million of these frames and get the answer back, but that's not really, what would be ideal is to be able to tell what it is with the noise in there. So an analogy for this is a game that is very difficult to win. That's why I call it a game for losers. So the goal is to guess what the value of the blue dice is. So we roll 1 blue dice and 2 white dice. But the key is you can only see the sum of the 3. So this part is hidden and you only see the sum and you have to guess what the blue dice is. So in this case, we rolled a 2 on the blue dice and we get 6 and 2 on the white dice. And so the total is 10. And I tell you, the player, we rolled 10 with the 3 dice. What did the blue dice roll? So, it's very hard. You can guess it's really hard to win at this game. And the analogy for this is that the blue dice is the signal you're looking for. And then the white dice is the noise that's added by the detector. So the noise is actually bigger than the signal. So if you want to give it a try, you can try. I have 2 more rounds down here. And we rolled a 9 and a 10. So if you think you can win at this game, give it a shot. I'll show you what the answer is in the next slide. And I hope you don't think you can win, because you can't. In this case, it was a 1, and then in the other case, it was a 3. So again, it's impossible to tell. So how to win at this game, though, is you cut a deal with the dealer to multiply the value of the blue dice by 100 in advance, but not the white dice. Now it's really easy to win. So, for example, we have a sum here of 205. Here we have a sum of 108 and a sum of 510. So we know that the 2 white dice can only generate something like 5 to 10. Let's see, 2 to 12 electrons. So if you get 200, you must have something going on with the white dice. So indeed, in this case, we'd have 2 on the white dice, 1 in this case, and 5 in this case. And this is the idea behind these infrared arrays called Avalanche photodiodes. You have your photons come in, they hit an electron, and then you use some circuitry to take 1 electron and turn it into a multiple of it, let's say 100 times, and then you read it out. So in this case, just like the dice, we had our low signal of 2, then we multiply it by 100, so we get 200, then we add 8, and we get 208. So in that case, it's very easy to tell what the true underlying signal is. This is the more detailed view of the whole thing. The right image shows the photon getting absorbed in, this is 2 pixels in our detector, which has 1 million pixels. It gets absorbed, creates an electron, then passes through several different regions in the pixel. The pixel in this case is going from front to back. First, the electron is created, then passes through a special type of electronic junction. And then finally, it goes through this multiplication region, which multiplies the number of electrons by a fixed amount. In this case, it looks like about 20, which is called the gain of the device. And finally, the electrons are moved into this yellow circle region, which is an electronic contact where they can get read out. So comparing what you can do with this technique, this is what a perfect detector would do with the low flux field of 1 photon. So you can sort of see the cat. Then you have this noisy detector image. But then when you use the noisy detector with this avalanching process, you can actually do a very good job of recovering the cat, nearly as good as you did with the perfect detector. So that's the work we're doing here at This is our Hilo facility where I work. I should say this work was started by Don Hall, a professor shown at the bottom left, who sadly passed away last year. He had the original vision behind using these new detectors for astronomy and for what they could do. I'm also picturing the rest of our team here, Klaus and Shane, who are on the panel, Charles and Aiden as well. And also our partners in industry, including here in Hawaii. So we're working on developing these exact devices to here at the Institute for Astronomy in Hilo, and the goal is to put them on the next big space telescopes as the detectors of choice for the infrared camera. The ultimate goal, of course, is being this biosignature detection on planets like the Earth or on other stars. But it's a long way to go. We got our first detectors that were successfully built in July. This is a picture of our lab in Hilo. At the back here, I'm zooming in on this massive astronomical camera. That's about 5 feet tall, which we're using to test these detectors. This weighs hundreds of pounds, and it's got to be kept really, really cold, so to keep the infrared glow as low as possible, just a few tens of degrees above absolute zero. If you zoom in if you cut into the device, or take it apart rather, you can see the detector itself, which is this tiny sort of half-inch by half-inch square. It's surrounded by copper to reduce electronic and thermal noise. And all these hundreds of pounds of instrumentation around it are just to keep it cold and stable and let us read it out. So this was a sort of a first sort of bespoke device, and it took us quite a while to get it working. It was quite complex to communicate with the device. It took a lot of dedicated programming and debugging by our team. But we did get our first image out not too long ago. We rigged up a little test target in our lab, and we initially everything looked really good. You can see we can take an image, you can read the numbers, you can see the lines. It looks like most of the pixels were working, and there weren't any obvious bad areas of the detector. But of course, it's not just what you can see, it's really the noise level that's important. And when we first measured the noise, we found it was 1,000 times higher than where we needed it to be to detect extrasolar planets. So over the last, many months, I'm just showing kind of a jumble of pictures of the many different steps we took to try and get it to reduce the noise in these devices. I won't go into detail. I don't want to bore everyone, but just think of this, I say like a sort of, in martial arts movies where you have these montages where the trainee starts out with really weak technique, and then instead of showing months of painstaking work, they just compress it into 1 minute. But the net result is we've reduced the noise almost to the level where we need to be, so by a factor of 500. And I really want to give credit to our team members, Charles Antoine Claveau and Shane Jacobson, for the really brilliant insights they've had about different ways to do this. So we're really almost there. We can almost get this to where it needs to be. And currently it's performing better than any other infrared detector that's ever made, I think. So our next steps are to take it and put the instrument on sky. So we're going to connect the same lab camera that I showed before is going to be attached to the back of the University of Hawaii's 80-inch telescope on Mauna Kea, and prove that it, see what it can do, and we actually look at something other than some random target we rigged up in our lab. Look at something in space. And then after that, of course, the goal is to go to space. So we're submitting a proposal right now to launch these into space on a little suitcase-sized satellite to really prove that they can work in the harsh environment of outside of the Earth's atmosphere. So I guess I'll just leave with this image here. This is sort of a simulated image of what we'd expect to see if we were to take a picture of our own solar system from another star. You can see Jupiter, Venus, and Earth. And the sort of the takeaway here is that we want to take that little few pixels of light from an Earth-like planet, analyze it to see what it's made of and see if it could really support life and whether life really exists there. And one of the key aspects of this is just building detectors that are sensitive enough to do this kind of work. So I guess I'll end here. If anyone has any questions, I'd be more than happy to answer them.
All right, thank you, Michael. That was an excellent talk. So we have, for those who'd like to ask questions, if you're in Zoom land, please use the Q&A function and you can put questions up there. I think the chat is also open, so I think you can put it there as well. And I'm not sure if comments are enabled on YouTube, but I will take a look and try to see if there are any questions coming there. We already have one question. Looking at the instrument you mentioned for Luvoir, which you can also explain what Luvoir is. The question is, why are there 3 prisms inside that instrument instead of keeping it simple with just one?
Okay, so let me reshare if I may. And let me go back a few slides. Whoops. So let's go all the way back to that. So this is Luvoir. This is a concept of a space telescope that would let us study instruments like the Earth. So this one, there's an instrument on there which I showed called Eclipse. It stands for something which I don't remember, which was meant to do this kind of spectroscopy of extrasolar Earth planets that we were discussing. So the question was, why do we need 3 prisms instead of just one? And there's sort of a couple of reasons for that. One is, if you look at the way this prism operates, it spreads light, and the amount that it spreads light over different wavelengths is called the dispersion. And generally, in order to be able to see the lines well, you need high dispersion. So you need to take the light and spread it over a much bigger set of angles. And you can get high dispersion by stringing together 3 prisms together. So you multiply the power of the prisms to do that. And that lets you get the kind of accuracy you need to be able to see the lines of the sun. So for example, this isn't quite a fair analogy because you need lenses to do this as well. But you can see with just one prism here, you don't really see any lines in the spectrum. With more, you would start to get to the point where you could do that. It's not a perfect analogy. That's not 100% accurate because you do need lenses in the system as well, but it's pretty close.
Okay, thank you. Do we have any more questions to put into the chat? So here's a question in the chat. What's the expectation for when Luvoir might be launched, if it's even funded?
Okay, so that's a political question. So there are 2 sort of proposals that were put forth recently to the sort of luminaries of astronomy, who kind of set the course for the next 10 to 20 years. And one proposal was for a 4-meter telescope called HabX, and one was for a Luvoir, which is 15 meters. And so 50-foot telescope versus 12-foot telescope, very big difference. And the luminaries said neither of these proposals was a good idea, but they should work on something intermediate, something that's about 20 feet across. So this telescope does not have a name yet. It hasn't been designed. None of the instruments have been built. It's not HabX, it's not Luvoir. Some people have called it LUVX. That's just like the name that people have come up with informally. But in terms of time to launch a telescope like this, one of the things is that the technology isn't quite there yet. As I've shown, the infrared detectors that we're developing them to be suitable for a telescope of this quality that can do exo-Earth imaging, but they're still too noisy. And there's other very, very significant engineering challenges. So to solve all those engineering challenges is going to probably take 10 years, and then it would take another maybe 7 years to launch a telescope like that into space. So it's on the order of 10 to 20 years before a telescope like that could find another planet like the Earth would go into space. It's a long time, but it's an opportunity as well to develop all these technologies that will let us answer some really sort of profound questions about where we are in the universe as a living planet like the Earth.
Thank you. We do have a question from YouTube land. Why is the mercury cadmium telluride the material for the detectors? Maybe that's a good question for Klaus, since I think he discussed that in his previous talk, if he's here, but you're welcome to answer as well.
Yeah, if Klaus is here, he is the super expert on this.
I am here. A mercury cadmium telluride is a mixed semiconductor consisting out of these 3 metals. And its main advantage over anything else is that you can tune the, what is solid state physicists call the band gap. And the band gap is related to the wavelength range that these semiconductors can detect. So by changing the mixture of the mercury content and the cadmium content in the mercury cadmium telluride mixture, you can tune the wavelength range that the detector is sensitive to, and you can tune a number of other properties. Now, for simple detectors like the ones that are currently flying in the James Webb, there are two flavors of that mercury cadmium telluride material, two mixtures that are being used. One is sensitive out to 2.5 microns, 5 times the wavelength of visible light, and the other one is sensitive out to 5 microns, 10 times the wavelength of visible light, so twice the wavelength range of the others. They have slightly different properties. The shorter wavelength material has lower dark current, somewhat lower noise. It's better for highly sensitive observations. The other one is better for longer wavelengths that the other one simply can't see. And similarly for the type of detectors that Michael was just discussing, he showed one diagram of these pixels, and the pixels actually consist of different layers of mercury cadmium telluride tuned to different wavelength ranges with different band gaps and different mixtures, so that you can, for example, do this electron multiplication effect in a different material than the actual detection of the photons. So bottom line, this property of mercury cadmium telluride of being able to adjust it in its properties by changing the mixing ratio offers wonderful flexibility that no other semiconductor offers in the same way. So it's a wonderful material for these type of very advanced detectors.
Excellent, thank you. Okay, we have another question in the chat. So are ground-based telescopes using these kinds of technologies able to discover potentially habitable planets?
The answer is yes, not current ones, but ones in the future. There's current concepts for 30-meter telescope, 30-meter class telescopes, and those will have sufficient light gathering power and sufficient angular resolution, or you can think of it as image sharpness, that would let us detect Earth-like planets around stars not quite like the sun, but stars that are smaller than the sun, nearby ones. There would be an opportunity there, in principle, to measure Earth-like planets in the habitable zones of small stars. That is one of the main science motivators for building these telescopes.
Excellent. So as moderator, I'm going to take my opportunity to ask a question. You talked about Luvoir using this technology and finding habitable planets with Luvoir. Are James Webb's detectors, which are the previous generation that Klaus was describing, up to the task along with the smaller mirror that James Webb has compared to, say, the ELTs, the large telescopes that are planned?
Can you restate that question, Roy? I'm not sure I understood.
So we asked, you said that the TMT or similar large ground-based telescopes of the future could potentially discover habitable planets around smaller, cooler stars. How about James Webb?
Klaus, do you want to take it? I mean, you're the, or I can do it if you like. You're on mute.
James Webb has limited capabilities to image planets. I'm actually personally involved in one project to do spectroscopy, take spectra of exoplanets near within a few arc seconds of stars that are just barely separated. But James Webb has several disadvantages there. First of all, it was originally designed as a cosmology instrument. The original concepts of James Webb were developed at a time when the first exoplanet was not yet discovered. The whole exoplanet field developed while James Webb was already defined. So it's by no means optimized for that task. One problem is this segmented nature of the mirror that gives a very massive and messy so-called point spread function. Instead of a sharp image of a star, we get a somewhat blurry image with lots of additional features in the wings of that profile of a single star that can possibly interfere with the detection of planets. Dedicated planet hunting or discovery telescopes try to avoid those complicated patterns, but James Webb has them. Then the detectors are not quite as sensitive. So overall, James Webb is more limited to larger planets, and that's what our program actually tries to do spectroscopy of. Planets the size of Jupiter or larger that are still fairly early in their evolution and are therefore still quite hot, so that they're easily detected in the near infrared. So what we can do with James Webb is large planets, fairly young planets, hot planets. For something small and relatively cold, like the Earth, that primarily is visible in reflected light and not in its own thermal emission, the James Webb is not really suitable.
If I could just add to that. So the one thing I totally didn't talk about in this presentation was the technology to suppress the starlight. And that is an extremely challenging task, to take a star and suppress it by a factor of 10 billion, which is what you need to do to see an Earth around it. And there's been a concentrated sort of 10 to 15 year effort to build the technology to do that on space telescopes, which is soon to bear fruition in a telescope called Roman, which is a small telescope, too small to see Earths, but will be good enough to see Jupiter-type planets. So there's a whole other aspect of this work, which is starlight suppression and being able to, suppress a star without suppressing a planet, which is a major technical challenge as well.
Just to illustrate those numbers again, 10 billion in sort of mathematical terminology, that's 10 to the 10th, a 1 with 10 zeros. What James Webb can do is a lot less than that. It's 100,000. That's a 1 with 5 zeros. So in some sense, what we need to detect Earths is 100,000 times better sensitivity to faint light sources near bright ones, or the contrast ratio, compared to what James Webb can typically give.
Truly astronomical numbers. Okay, one more question and then we'll end it. In the Q&A we have, how are you planning to actually test the detectors that you're developing in space? You mentioned your suitcase satellite. So what's the procedure and what are you going to test it on?
Well, we're not going to look at planets that are around other stars. That would, for reasons that the last question probably brought forth, that's not going to be possible. But our plan would be to look at sort of free-floating planets, and those are you don't have to deal with this starlight problem, and you can look at them and analyze their light without this challenge. So what we'd be looking for is sort of light modulations of the planets to see potential weather patterns on them, that kind of thing. There's sort of two parts to this, I would say. One is, what can you do with a suitcase-sized satellite? The mirror is small, so obviously the things have to be pretty bright. And you'll never get the sensitivity to see something like an Earth with something like that. But the point of it is not just that. It's that if you can launch a detector like this into space and prove that it can survive in space, that in itself is a very important step, because in order to put a detector like that on a telescope that costs $10 billion when you launch it, you need to have 100% confidence that it can survive in the environment of space. And there's no better way to do that than to actually launch it into space before on something that costs $5 million, not 10 billion. And if it doesn't work, you've learned a valuable lesson. And you can understand, and that can help you understand how to make it survive in that environment. And if nothing comes out of it, you've paid a small price. Whereas if, it's an important step to take.
Well, we're looking forward to your future public talk where you'll tell us about the success of your suitcase satellite. So thank you again, Mike, for an excellent talk, and Klaus for helping answer questions. And keep an eye out on our social media for upcoming talks. And remember, next week, Wednesday, at 5:30, we'll have our final talk in this series, talking about using James Webb to study supernovae. Thank you, everyone, and have a good evening.
Thank you.
Goodbye. Oh, see you.